Binary search and recursion. So we are going to implement an example of a binary search algorithm, which of course will use recursion. Recursion right there. So first let me explain what binary search is. The problem is the following. You are given a sorted array of integers, like so, 20. So here's an array of sorted array of integers. You see they're sorted. The smaller one goes first, then the next bigger one, and so forth. And I ask you, okay, is the number 5 in the array? And if it is, you have to tell me the index of the number 5. In this case, right there it is. It's at index 1, so 0, 1, remember? And if it's not, say if I ask you for the number 22, you are going to check it's not there, and you're going to return -1. Uh, so that's the problem, right? So how would you do that? Well, you cannot, as a person, you can just sort of look at it, and basically what you're doing is you're going left to right looking for the number. But let's imagine that there's a million numbers. That's a lot, right? If you did that, if you started, you could do that. You could say, you could start from the left and go all the way until you find it, or until you get to the last number, the millionth number, and it's not there, and then you're done, you return -1. So the thing is, if you did that, then on average, you would take a time that is equal to the length divided by 2. Right? Because on average, you would get to halfway through the array, and so it would cost you array length, the length of the array divided by 2. So that's 500,000 for a million array. So for a millionth array, element array um, takes 500,000, right? So is there a better way? Well, they are sorted, right? So if you have a million numbers, like this, imagine this is a lot bigger, you could just go to the point in the middle, or the array index, 500,000, and you could say, well, is that number, say I'm looking for the number 222,000. So is the value at this position, this value could be, 123, like that. Is the value at that position bigger than the number I'm looking for, 222,000, or is it less than it? Well, in this case, 123,000 is less than 222,000, right? So, what does that mean? That means that the number I'm looking for must be somewhere between A of 500,000 and A of a million, right? So basically I take the array, I look at the number in the middle. If the number I'm looking for is bigger than the number in there, so if I'm, in this case, the number in the middle is 8, say I'm looking for the number 13, 8 is less than 13, so I know that the number 13 must be somewhere in between here and here, at the end of the array, if it's there at all. On the other hand, if I was, say, looking for number 2, I look at the number here is number 8 in the middle, so I know that if the number 2 is in this array, it must be anywhere between the beginning and here. So I can basically just, if I'm looking for the number 2, I look here at the number 8, I can discard this whole half. And and then this is now, all I have to do now is look for the number 2 in this array, the array from the beginning to the middle. But that's really the same original problem, right? Is the number 2 in this now smaller array? And so I recursively call myself. I say, okay, well, let's repeat the whole thing, but only on this first half, right? So that is binary search. We look at the middle number, and then we proceed either with the first half or with the second half, and recursively do the whole thing again. We take the array, we look at the middle number of that array, say 10, and then we look at the first half of the second half. Notice that there's this problem with, If you have an even number, there is no middle. So we're just going to go with the one to the left of the middle, 10. Okay, so let's do that. So I'm going to go for the public static int binary search, and it's going to take an array A. So A is going to be, or the array, and the value that I'm looking for, and then the low or the start and end of the array. Let me put a little Java docs. Looking for value, the array, the value we are looking for, start, B, start index of the search, start, and then the end is the end index of the search. So basically we're going to be searching for A start to A or array end. We're going to be looking from array start to array end, and it's going to return the index of the index in array where value is stored, or -1 if value is not in array. And this of course assumes that the values in array are sorted, small to big. Okay, so let's start with sort of the easy case and say, well, we usually in when you're doing a recursive function, you want to often start with the base case. That's often easier. So the base case is when the start, the end minus start. Oh, let's do this one. If n equals start, right? So that basically means that the n equals the start. So the array I'm searching for is just one element. So what I can do is I can say, well, if array of start equals value, then I'm going to return value. I'm sorry, I'm going to return the index, which is start. Otherwise, I've got semicolon. I'm going to return. I'll put that in a new line. -1. So this is the case where the array has only one element. Array has only one element, right? And we should also do, the other one is the case where it has two elements, just because it's easier to do that now. So if n minus start equals 1, if the n minus the start equals 1, right, so that means that there's only one difference of 1, then I have to compare, I have to basically check both of them. So if array of start is value, then I'm going to return start. If otherwise, if array of end is equal to the value, then I'm going to return the end index. Otherwise, it's not in neither one of them, so I'm going to return -1. Right. So there you go. One of the things, this is array of size 1. Okay. So it's not that the array itself is of size 1, but the part of the array that we're looking is the part between start and end, and because the index, this is say 5 minus 4, so the array is actually on, sorry, on size 2. The array is of size 2. That works. Now, when you see this, if you look at this and you look at this, you realize that you don't need this part anymore, right? If you change this to this, if I change that to if n minus start is either 0 or 1, that is either 1 or 0 or 2, or negative, but we're going to assume that never happens. Then we can get rid of all this. Right. So just to go over this, we can test it. Let's just test this to show you. So I have an integer array. A is, now this is only going to work for that. For arrays of size 1 or 2, and I need to put a return value here. So just going to put that there for now. And I'm going to print binary search of array values. Start is 0 and end is a.length minus 1. And array is going to be a, and say we're looking for the value of 1. You can save that, run it, I get 0, so which is actually right. So I'm looking for the number 1 in this array, which is at index 0. Let's say I was looking for the number 2, I run it, I get an index of 1, there's a number 2. If I do 8 and 10, I'm looking for the number 2, it's going to be minus 1, because the number 2 is not there. I can do that, change that to 2, that should be 0, okay. So I'm just doing a little bit testing to make sure that my little program worked for arrays of size 2. So I'm looking for the number 2 in the array of 4 to 9, and that is not there. And let's look for the number 9, and that should be index 1, so that works. It looks like it works. Of course, if I put an array 3, then it's gonna get minus 6. Doesn't work. So because I haven't done that, so that is gonna be the recursive. Okay, so this works right now for arrays of size either 1 or 2, right? Because all it's doing is if you have an array of size 1 or 2, or the start and end is of size 1 or 2, it just checks, is it the first one? Yes. Is it the second one? This one checks the first one. This one checks the other one. If they're both the same, then this is the same as that, so it would have returned this, and we just end up checking it twice. Not a big deal. But what if it's of size 3? Well, we're going to need the midpoint. So if it's bigger than that, the first thing we're going to do is we're going to calculate the midpoint, like so, right? And so we calculate that's the midpoint in the array, right? This point here, the index of it. And now we need to say if the array value at midpoint, if that number, say I'm this is this number. So I'm saying I'm looking for the number 2, and I get this array midpoint is 8. So if midpoint is bigger than the number I'm looking for, which is the value, so if 8 is bigger than 2, I'm looking for a number 2, then I'm going to look for on the first half, right? So then I'm going to return a binary search of the array of the value in the first half. So the first half is between 0 and the midpoint. Otherwise, it's going to be bigger than or equal, and I'm going to return the binary search for the array for the value from the midpoint to the end. You see I'm using the midpoint twice. Again, it's a little bit of wasted computation. Probably put +1 there, but just for now, just to make it clear, right? If the midpoint is bigger than the value, I go this way, the first half. Otherwise, I go the other way. So I'm going to recursively call myself here. And you see what's going to happen is, notice the binary search call, these two values are always the same, right? So the first two values never change. Seems a bit wasteful, but we need to do that in order to get a hold of these values on every call. So you just keep passing them and on and on and on. However, these two change, right? So when I call it this is between 0 and midpoint, and when I call here is between the 0 and the end. And notice that I'm going to only call either this one or this one. Okay, so let's run that. And now we get a value of 1. So let's see, I had this array. I was looking for the number 9, and indeed the number 9 is at index 1. So I could put 4, 7 there. I could run it again. Now I do find 9 is at index 0, 1, 2, 3, 3. So it does seem to be working. Let's look for something that's not there, like number 1. That returns -1 because it's not there. And so you should do a lot more testing with this kind of program. I'm sure it's not really working correctly for all cases, even though it seems to be, because I haven't done enough testing, but it's pretty close. At least it works for these cases. So, what's the advantage of that? I didn't finish this part. Again, if you have a million, because we are dividing it by half each time, so the first time we look from, we start with an array, say if this was an array of a million element, we would start with a million, then half a million, then half of half a million, 250,000, and so forth. You know a little bit of math, you know that what we're actually doing is the number of times it gets called is the logarithm base 2 of 1 million. 1, 2, 3, 1, 2, 3, and I don't have my logs here, but anyway, it's right here. You can see it's going to be 4, 8, 8, 16, 20. It's going to be 20. The log base 2 of a million is 20, or it's 20 something. So we can I can do the basic calculator here. Nope. In the scientific calculator, 1 million, 1, 2, 3, 1, 2, 3, log base 2, yeah, it's about almost 20. So what does that mean? That in this case, 1 million takes you just about 20 calls, 20 checks. So if you do it linearly, it would take about 500,000 checks. Check the first, check the second number. If you do it using binary search, you only have to do it 20 times. So the difference between 20 and 500,000 is a lot, right? You have 20 bucks versus $500,000. Big difference, big difference in computer time also. So in terms of the recursion, you see that hopefully this is, fairly easy to understand, right? We have why we need recursion here. So we started with this base case here. We have a base case for arrays of size either 1 or 2, and then we have a recursive call that says, okay, the array is too big, so I'm going to split the array, but I'm only going to search either the first half or the second half. And I'm recursively calling myself each time with an array that is going to be half as small as the previous one. Therefore, eventually I will get to the base case. And hopefully this is, if you look at it, you can see why we need recursion and why implementing this without recursion would be, the code would be quite a bit more complicated or hard to understand. Well, if you look at it this way, you say, okay, clearly I'm just going to call myself, just do binary search again between these two values.